Yes, now I'm recording. What I want to do in the Zoom meeting is go over some of the questions that are on the practice exam. We won't have time to do all of them. I think there are about 20 or 21, something like that. But we'll look at some of them. And this will get you started on the problem, show you the equations that you'll need for that problem, and then you should try to do the problem yourself. Do the problem and check your answer against the published answer. So here's a problem. It's question number 2. By the way, the numbers in the problems that I'm showing here in the Zoom meeting may not be the same as the numbers in the problems that are published, which have the answers corresponding to those numbers. So you got to be careful to make sure you're using the right numbers. So use the published final exam, which includes answers, to get the questions, solve the problem, and then check your answer. So in this question, 2-point charges are positioned in the XY plane. There's Q1 and Q2. They are given the values, Q1 and Q2 are charges, so they're coulombs. The question is, what's the size of the electric force? And I guess when it says size, that probably means the magnitude. So without worrying too much about the direction, what's the magnitude? And then the second part has to do with the direction. The question is, what's the X component? Well, you know that the magnitude of the Coulomb force is K Q1 Q2 over R squared, where K is a universal constant, 8.99 times 10 to the 9th in SI units, Newton meters squared per Coulomb squared. Q1 and Q2 are given. K is a number that I think is written on the front of the exam. R is the distance between the two charges, and you have to get that from the picture. So you see this charge is located at 60, 30 millimeters. This charge is located at 30, 80 millimeters. So R is the square root of delta X squared plus delta Y squared. You remember to convert it into meters by the Pythagorean theorem. So now you just use your calculator to calculate that number. What's the X component? Well, in other words, they want the X component on the charge Q2. This is the charge Q2. They're both positive charges. So evidently there'll be a force in this direction. And that's the force vector. And now I can separate the X and Y components by projection onto the X and Y axes. So if I look for Fx, so this would be the X part of it, I can define this angle. I can call that angle theta. And so F on 2 in the X direction is F cosine theta. And what's the cosine of that angle? Well, it's the same as this angle. You know, if I look at that vector, it's the same as this angle. So I can get that from the geometry. It'll be delta X over R. So it'll be X2 minus X1 over R, where again, X2 is, I guess, looks like 30, and X1 is 60. So X2 minus X1 is minus 30. That's in millimeters. F you already calculated in part A, and you also have to divide by R again. So it'll come out negative. You see it's negative. It's back in this direction. So it has a negative x component. Now these are multiple choice questions. So you'll find you should find the number you calculate is one of the choices in the multiple choice question. All right, that's a simple problem from early in the semester, just the Coulomb force. Let's see if I can. Here's the next question, or well, the next one I have for the Zoom meeting. Question 4. The circuit shows a battery, 18 volts, and 4 capacitors, C1, C2, C3, C4. And those capacitors are given, they're all different, they're all in millifarads. What's the equivalent capacitance of the 4 capacitors? Well, to answer that question, you don't need to know the voltage. The voltage is sort of irrelevant. Now, you remember, and this should be written on your help sheet, the equation for capacitors in parallel, the equivalent capacitance is just C1 plus C2. And the equation for capacitors in series, C is C1, C2 over C1 plus C2. Or you could say 1 over the equivalent capacitance is 1 over C1 plus 1 over C2. Now you have to identify what combinations do we have here. Well, first of all, these two are in series. So there'll be a combination of C1 and C3. And these two are in series. So there'll be a combination of C2 and C4. So C13 will be C1, C3 over C1 plus C3, just like here. And C24 will be C2, C4 over C2 plus C4. And now the equivalent capacitance for the 4 capacitors will be like this. This is C13. I've kind of combined those into one equivalent capacitor. This is C24. I've combined those into one capacitor. And now these are in parallel. So C13 is parallel to C24. Because any current coming in here will split apart. Part of it will go into C13, part of it will go into C24. It's not going into C13 and then into C24. It's going parallel into the two sections. So C1234 will be C13 plus C24 capacitors in parallel. Here's another problem involving electricity and electric currents and electric circuits. A voltage of 14 volts is applied across the two ends of a cylindrical wire of length L, radius R, and resistivity rho. And then there's a current of 1 amps. So you have this wire, and when you have a potential difference delta V, where let's say this is the high potential side and this is the low potential side, there'll be a current I in the wire. Now you make a change Now you change the length to 7L, the radius to 3R, and the resistivity to 8 rho. Now what's the electric current in the second wire, which will be longer and larger in radius. So it'll be 7 times longer. It'll be larger in radius by a factor of 3, and it'll be made of a different material. Now, same delta V. Now, what's that current? So this is sort of current number 1, and this is current number 2. This is what you're trying to calculate. Now, these are the equations you know. I is delta V over R. That's Ohm's law. And R is rho L over A. Remember, that's the formula for the resistance of a wire with length L, area A, made out of a material with resistivity rho. So these are equations you should have on your help sheet. Now A is pi R squared. So to answer the question, it's just a matter of proportionalities. I is proportional to 1 over R, because delta V isn't going to change. I is proportional to 1 over R. And 1 over R is proportional to R squared over rho I. So I is proportional to R squared over rho L, I should say, rho L. So I2 will be I1 times rho 1 over rho 2, L1 over L2, R2 squared over R1 squared. And now rho 1 over rho 2 is 1 over 8. L1 over L2 is 1 over 7. R2 squared over R1 squared is 9 over 1. So you just have to calculate 1. Well, I1 is 1. So you just have to calculate that number. That'll be the answer in amps. All right, so one more question involving electric currents. You have this circuit. It's a 2-loop circuit. It has a battery with potential 15.3 volts. And the 5 resistors all have the same resistance. They all have resistance 5 ohms. So there are 2 numbers in the problem, the 15.3 volts and the 5 ohms. And now the first question is, what's the equivalent resistance of these 5 resistors? Well, again, you should have written down the resistance of resistors in series and resistors in parallel. Now let's identify resistors in series and resistors in parallel. You see, these 2 resistors are in series. Any current that goes into R2 will also go into R5. So R2 and R5 are in series. And so the resistance, the equivalent resistance of 2 and 5 is R2 R5 over R2 plus R5. Now, that resistance is in parallel with this resistance, R3. So we'll add R3. We'll have like this. We'll add R3 and the combination R1 and R2, R2 and R5. So here's 2 and 5. The resistance of 2 and 5 will just be 2 times R, because you just add the resistances. And now that's in parallel with R3. So the resistance of this combination will be, well, let's calculate 1 over R plus 1 over 2R. That'll be 3 over 2R. And then it's the reciprocal of that. Now you have equivalent one resistor. R1, R235, R4. You see, R1 and this combination of three resistors, which I could think of as one equivalent resistance, 235, that's in parallel, in series with both R1 and R4. So the equivalent resistance is R1 plus R235, which is 1 over R3 plus 1 over R2 plus R5. Then the reciprocal of that, that's the resistance of this combination of three resistors, plus R4, because that's in series. And that turns out to be 8/3 R. Now there's a part 2 to this question, which I don't have. Oh yeah, I do have it written down here. Part 2 of the question is, what's the power dissipated by resistor R4? Well, you have to think about what the currents are. There'll be a current here coming out of the battery. That's a current I. That same current will be coming back into the negative terminal of the battery. So that's also current I. That current is delta V over R equivalent, because all of these 5 resistors can be combined together into one equivalent resistance, 8/3 R. So then the current goes through a resistance of 8/3 R. That means delta V is the current divided by 8/3 R. So, well, that's the current. Well, what's the power? Well, the power is I squared R. So again, this is an equation you need to remember or have it written down on your equation sheet. Power is I squared R in a resistance. So I is V over R equivalent squared times R4, and that'll turn out to be some number times V squared over R. So go home and do this problem, and then check your answer against the published answer. All right, so those were all problems having to do with current and voltage and so on. Let's go on to some of the later problems. Here's a problem having to do with magnetism. There's a toroid with 2,350 turns of wire. So first of all, you have to know what a toroid is. A toroid is a donut. So here's the hole in the donut. And now there's a winding of wires around the donut. So let's put the windings, let's put the coils of wire in a different color. So there are coils of wire here. And it comes down and comes back. And so it's like a solenoid, only a solenoid is wire wound around a cylinder. Well, it's not like this. It's the wire comes up here and goes down into the hole. Wire here goes into the hole. So that's a toroid. Now, there's current around these wires. So let's say the current is in this direction. So there's a current I. And there are n turns of wire. So n turns. 2,350 turns. And the inner radius is given. So there's an inner radius. Try a different color. So there's an inner radius like this, R1. And there's an outer radius like this, R2. Now, you know, current creates a magnetic field. So the question is, what's the magnetic field? It'll depend on the radius. What's the magnetic field? It's going to be cylindrically symmetric, so we just have to pick one radius. What's the magnetic field at the midpoint between R1 and R2? In other words, what does it say? Halfway between the inner and outer radii, inside the torus. And I is given. And the way to solve this problem is to use Ampere's law, apply Ampere's law. You say the integral B dot ds, that is the circulation of B around any closed curve, is equal to mu zero times the amount of current going through the curve, through the surface bounded by the curve. So let's choose, let's make it, so here's the Amperian loop. The Amperian loop will be at this radius. So the Amperian loop will be a circle at that radius. So that's the curve C. I suppose this problem is probably worked somewhere in the book. If not, I'm sure you can find it in the final exam review, in those review pages. So the circulation of B, well, the magnetic field is going to be around the toroid, just like in a solenoid, it's inside the coils of wire. So the B phi, the magnetic field circulating around inside, times the length, 2 pi r, the circumference of the circle, is mu naught times the total current going through the surface. Well, you see, each coil of wire goes through the surface. So there's a current I guess it's called lowercase I, for each wire, and there are n wires, there are n turns of wire. So it'll be n times I. And now you're supposed to calculate B. So mu naught Ni divided by 2 pi r, and R is 1/2 R1 plus R2, halfway between the two, the inner and the outer radius. So this is a case where you have to know how to calculate a magnetic field when you're given a current. Here's a little bit different problem. An RLC circuit with an AC generator. So, you know, this is a problem from, so you have this generator, and then you have a resistor, an inductor, and a capacitor. This is from the chapter on electromagnetic induction. The inductor will slow down the charging of the capacitor. Oh, but this is not charging the capacitor. This is an AC circuit. So it has some frequency. This is a graph as a function of the frequency. And you see there's, well, what's plotted on this axis is the current, the RMS current. The current will be an alternating current because you have an alternating AC generator. So you'll have an alternating current. What's plotted here is the root mean square value of the current. So it's the average of I squared. I is alternating between I, some maximum value I max, and minus I max. I squared alternates between 0 and I max. The root mean square will be 1 over the square root of 2 times the maximum current. All right, well, we have this resonance. So this is a famous property of RLC circuits. It's the resonance. Now, I don't have all the equations written down for RLC circuits, but again, this is something you probably want to have on your help sheet, is the equations for an RLC circuit. You know, what's the impedance? What's the resonant frequency? What's the root mean square current at resonance? So here's the resonance. So the resonance occurs when the driving frequency is equal to, looks like 500 hertz. So when the driving frequency is 500 hertz, you have the resonance. Now, what are we supposed to calculate? Well, we're supposed to calculate what is L. Oh, and it tells you what is C. So the capacitor is given 316 nanofarads. Question is, what's the inductance? Well, we see from the graph that the resonance is at 500 hertz. And you probably remember the resonant angular frequency is 1 over the square root of LC. So at resonance, omega is 1 over the square root of LC. Now, F is not the same as omega. Omega is 2 pi times F. So this is the angular frequency, 2 pi radians times 500 hertz. That has to be 1 over the square root of LC at resonance. Well, okay, I can see from the graph, this is 2 pi times 500, so I can solve for L. So that's actually part 1 of question 14. What is the value of L? It only depends on knowing the resonant frequency. There's also a part B. Now, I'm not sure I remember what the question is in part B. What was the question in part B? You remember, let's see, you remember the impedance is equal to the square root of R squared plus XL, the impedance of the inductor, minus XC, the impedance of the capacitor, squared. And the resonance is when XL is equal to XC. So at resonance, this is 0. And that gives you the minimum value of impedance. Maybe part B was the question, what's the resistance?
Oh, there was no part B for this question.
There's only that one part? Okay, I thought there
Yeah,
was.
there's only one.
Okay. All right. Well, anyway, there'll probably be a problem on the exam about the RLC circuit. So make sure you have the, the equations relevant to an RLC circuit written down. I think there was a question of that sort on the midterm exam. All right, now question 15. So this is going on towards the end of the semester. It has to do with electromagnetic radiation. So it'll be something about electromagnetic waves. It says the intensity at a distance 1 astronomical unit from the sun is 1.368 times 10 to the third watts per square meter. So I have here the sun, and you have a little square meter out here, and the sun is radiating light in all directions. And the question is, what's the total power produced by the sun? What you're told is the energy flux, energy per unit time per unit area at some distance. This distance is 1 astronomical unit. That's the distance from the sun to the earth. So this number, 1.368 times 10 to the third, is called the solar constant for the surface of the earth. All right, so the first question is, what is the power of the sun? Well, the sun is radiating in all directions. And the energy is conserved. So the energy spreads out around a sphere. The area of the sphere is 4 pi r squared. So at distance r, the intensity, so that's S, is the total power of the sun divided by 4 pi r squared. So this is like the total power divided by the total area. Well, the flux will be the same in all directions. And so no matter where you put the 1 square meter, it's going to be the same amount of power going through that 1 square meter. So to calculate the power through that 1 square meter divided by its area, 1 square meter, I just take the total power divided by the total area that the energy is being spread out into. That's 4 pi r squared, the surface area of a sphere. So that question is simple. It's just 4 pi r squared S. And you're given R as 1 AU, and you're given the value of S, solar constant. Now there is a part B, I think, in this problem, which if I remember, suppose you're not at the surface of the earth, but you're out here. So suppose you have a satellite out here with a solar panel. So this will have some larger radius, R2, from the sun, distance from the sun. And you're trying to calculate, I think you're trying to calculate the power going through that solar panel, or the power hitting that solar panel. So you want the power hitting the solar panel. That'll be the intensity at that distance times the area. Because remember, intensity is power per unit area. So intensity times area gives you power. And I think just as one little more wrinkle in the problem, it also says the solar panel has a certain efficiency. So this will be the total power hitting the solar panel, but you don't get to use all of that power, or the satellite doesn't get to use all that power. The satellite only gets to use a fraction of that, which is given by the efficiency times the power incident. So again, do this problem at home. Try to do this problem yourself without looking up anything, and then check your answer. That'll be a practice for the exam. The next problem I have here is problem 18. It has 3 parts. It has a diffraction pattern. So this is a problem on wave mechanics, or sorry, wave optics. It's diffraction. But this is kind of a hard one because it's got 2 kinds of diffraction. You have a set of narrow vertical slits. So the picture looks like this. Here's kind of a top view. Here's a screen, and it's at a distance d from these slits. So here, there's a screen with openings cut in it. So those are the slits, and this is kind of a top-down view. And now you have waves incident on this set of slits, and now you'll have waves coming out and interfering. So there'll be an interference pattern. Let's put the interference pattern in a different color. So there'll be an interference pattern here. Looks like this. There'll be, there'll be that interference pattern. Now, these slits have a certain width. What information are you given? You're given the distance from the slits to the screen, 2.95 meters. You're given the wavelength of light, 470 nanometers. You're given the distance between the points, between the peaks in the diffraction pattern, so call that dx. And now there are 2 parameters of this set of slits. There's the distance between the slits, or the spacing, and there's the width of the individual slits. So the first question is to calculate the spacing. And then there's going to be another question about how wide are these slits? Now, I wasn't really able to do this problem exactly, but it's fairly easy to do the problem approximately. And since this is a multiple choice exam, you don't have to have the exact answer. You just have to have a good approximate answer. And then you pick the choice which is closest to your approximation. So it's fairly easy to figure out the spacing between the slits. If you think of this as approximating a diffraction grating, you can just use the grating equation. d sine theta is m lambda. And what's d? D is the distance between two slits. So d is the spacing. Maybe I should have called that s for spacing. D sine theta is m lambda. Now that's the diffraction. Those are the maxima. Those are the bright directions with the highest intensity. Dependent upon the distance between the slits. So you're sort of assuming that the slits are extremely narrow. So it doesn't depend on the width of the slits. And that would be these large peaks here. So you see the central peak is at 0. The first bright fringe is a distance 1.4 centimeters. It says the tick marks are 1.4 centimeters apart. So this distance is 1.4 centimeters. That's the 1.4 centimeters. All right, well, so, you know, sine theta, so m is 1 for the first fringe. So sine theta is lambda over d. We're trying to calculate d. So d is lambda over sine theta. Now, again, I can calculate this very easily if I assume, if I make an approximation, I can say, well, theta will be very small. So sine theta will be approximately the same as theta in radians. So I could just say delta theta is lambda over d. You know, the sine of theta is the same as theta if theta is less than about 30 degrees. So for m equals 1, sine theta is lambda over d. So d theta is about lambda over d. And now by the geometry of the picture, d theta is dx over d, over this d. So I have an angle here. I have a little bitty angle here. It's about, you know, making an approximation, it's about this distance divided by this distance. More precisely, that's the tangent of theta. Delta x over d is the tangent of theta. But if theta is small, then tangent of theta is about the same as theta. So you see, I get a very simple equation for the unknown, which is d. D is lambda times capital D divided by delta x. So D is lambda, that's that 470 nanometers, times D, 295, divided by, I guess it's 1.5 centimeters. And so I get a number like this, 9.24 times 10 to the minus 5. Now, actually, if you look at the choices in the multiple choice question, that's not one of the choices. But it's very close to one of the choices. One of the choices is something like 9.4 times 10 to the minus 5. That's in meters. So, you know, you just look at the choices, you say, well, I've only calculated this approximately, but I'll take the choice which is closest to that approximate number. One of the choices is 9.4 times 10 to the minus 5. The other choices are nowhere near 9 times 10 to the minus 5. So I know, well, it must be that one. Now, the other questions have to do with the diffraction through the slits, which are in fact not terribly narrow. So if I draw a picture again, you know, I have a slit here, which has a width W. And I want to know what is the width. What is that width? That has to do with the other aspect of this diffraction grating. You see there's a big central peak, but then there's over here a little fringe, and over here a little fringe, not nearly so intense. And there's a point here where the intensity is 0. So there's a dark region at a certain angle. Well, it's given in terms of the spacing, but at a certain spacing, which is equivalent to the angle by this equation, there's 0 intensity. In other words, there's a dark region. And that depends on the formula for diffraction through a single slit. Single slit diffraction with a width. So again, you can apply the formulas for single slit diffraction through a slit with width W, given the angle or the distance to the first dark region. And if you look carefully, it's 1, 2, 3, 4, 5 tick marks. So it's 5 times 1.5 centimeters. It's 7.5 centimeters is the width of the first dark fringe. So again, you could approximately use the equation for single slit diffraction to get an approximation for the width of the slit. I don't know if it's possible to get these numbers exactly. Well, yeah, I'm sure it is possible to get these numbers exactly, but that's a more difficult calculation. So I would say, do this problem and see if you get the answers. And you might not get the exact answers in the multiple choices, but you should have one of the choices very close to your answer. That's the one you would pick. Review this by looking at the final review, pages 25 and 26. You can look in the textbook in the chapter on wave optics, but it's probably easier if you look on the final review, which has everything kind of in a more succinct form. The problem that is worked out in the book is two-slit interference. But this isn't exactly two-slit interference because it has many slits. So it's not quite the same as two-slit interference. It's not quite the same as single-slit interference, although this part of the diffraction comes from single-slit interference. It's not quite the same as the diffraction grating, because in a diffraction grating, you assume that the grading lines are very, very narrow. Here, they're not so narrow. So I'm not sure. Maybe the exact solution is not really what's intended on this problem. But if you look in the final review, it's on pages 25 and 26. You should see how to do, well, this is part A. There's also part B and part C. Okay, so I've got one more problem here. Question number 21, I think it is. So now this is one of the problems on relativity. There are several problems at the very end on relativity. This is the last week of the course. This one is a little tricky. This one says, when studying the optical spectrum of a very distant quasi-stellar object, they have found that a certain spectral line appeared at a wavelength of 646 nanometers instead of the regular 485 nanometers. In other words, there's an atomic transition which produces a certain color of light. That particular transition produces a certain spectral wavelength, which in the laboratory would be 485 nanometers. But the light from the quasar for that transition is not 485 nanometers, it's 646 nanometers. It's a longer wavelength. And so now you're supposed to calculate the radial speed of the quasar. Now, the numbers that are given in the sample exam that has the answers are not 646 and 485. They're 606 and 461. So try to do this problem, but use the numbers that were given with the practice exam where you can check your answer. Now, this is called Redshift, so maybe you immediately see, oh, this is an example of a Redshift, an example of a Doppler effect for light. You know, even for sound, the frequency changes depending on the velocity of the source. Well, the same is true for light. The frequency changes depending on the speed of the source. It's not exactly the same formula for the Doppler effect for sound and for light. It's different for light. But anyway, the equations for the Doppler effect for light are on the last page of the, not the final exam, the final review. That final review page on Lon Kappa has this equation for the Doppler effect. So let's see what it is. F is F0. That's the value of the frequency in the lab times the square root 1 minus C over V over 1 plus C over V. So you may not remember this. You may have to have this written down on your help sheet. So F will then be less than F0. It'll have a lower frequency. That means it'll have a longer wavelength. This equation is given in terms of frequency, but I can relate frequency to wavelength because frequency times wavelength is the speed of light. Speed of light's always the same, 3 times 10 to the 8 meters per second. So I can rewrite this equation for wavelength. So the wavelength in the lab is 461 nanometers. The wavelength observed in the telescope is 607 nanometers, put in a value for the speed of light. The frequency in the lab would be C over lambda 0. The frequency in the telescope would be C over lambda. And now you have to solve this equation. F is F0 times the square root, 1 minus beta over 1 plus beta. And you solve for beta. Beta is V over C. I think I have that wrong, don't I? Yeah, this part is wrong. This is what's wrong. This is V over C. So this is V over C. V over C is beta. So V over C. So, you know, this is just a simple algebraic equation to solve. We just solved it here with a computer program. And so it comes out to be some number between 0 and 1. That's the redshift, is the change in the frequency. All right, well, that's all I had prepared for tonight. Any questions you'd like to ask? Just unmute your microphone and ask if you have a question. All right, well, we spent about an hour, so I guess I will, let's see, I want to stop the recording.